Hello everybody, my name is Ayurchan from Japan, actually from Mongolia. As of this speaking, I'm doing my PhD in Nagaoka University of Technology, Japan. Today I'm going to give you my presentation about application of the lattice-Boltzmann method to liquid-solid phase transition in free surface flow using an example of Mongolian small hydropower plant. I presented this presentation on the 61st conference on hydraulic engineering a couple of days ago in Kyushu University, Japan. During the presentation, I recorded my presentation, but sound and video was not good, so I decided to do it again. So let's go. This presentation gives information about the main problem, a method to solve the problem, validations, application to the problem, summary of this work, and single slide for the future and the ongoing works. So simply, water turns to ice when temperature goes down below 0 degrees Celsius. Everybody knows that. Ice is common in cold region in winter time. For example, there are three types of river found in Mongolia, like partly frozen river, ice-covered river, and completely frozen river. Those natural phenomena is very interesting to understand the physics based on the numerical method using the mathematical models. Also, we can found that ice is problem where people work or live. So the main problem is how to model the ice phenomena in natural condition using numerical model. So an example problem today is the open water forming mechanism in outlet of the hydropower plant. So we will talk about it later. To accomplish our purpose, we need two modeling tools, a free surface modeling and heat transfer modeling with phase transition. Each model followed by general ingredients and highlights for them. For example, for the free surface modeling, we use lattice-Boltzmann method with the BGK collision operator and free surface algorithm, subgrid scale turbulent model, and forces incorporated also, and immersive boundary method is used for the liquid solid interface, while for the heat transfer modeling we use thermal lattice Boltzmann equation, and local enthalpy F-state scheme is in operation, and liquid fraction estimation. This will be used for the immersive boundary method in free surface flow, and non-Bosnian approximation for the water density, because the water is different from the other phase change material, because the density and temperature relation is different. And then these two models are already existed model in lattice-Boltzmann study. So only we have done is merging them into single complex numerical model. So we have proposed numerical model that is poorly formulated in lattice-Boltzmann framework. So this is the general scheme for general numerical scheme for the liquid solid phase transition in free surface flow. In a figure you can see the D2Q9 lattice arrangement, and on in the figure B you can see the grids, where we can see each grid is indicated by material as solid, wall, gas, interface, and fluid. Free surface is represented by interface cell. Interface and fluid cell consist of ice and water. Depends on the value of the liquid fraction LF. Main two equations need to be solved are shown below for fluid flow and scalar field. So these two equations coupled to each other based on the physical relation, like Frank number. First, we validated each model separately. For example, Dambrick problem for free surface flow, and 1D Stephen problem for heat conduction and phase transition. 2D melting of ice problem is used for validating heat conduction, heat convection, and phase transition. This is the animation of the result for 2D melting problem. This is the heat convection, heat transfer modeling. The problem is natural convection of water, and this animation is for the free surface flow. We have done several experiments on the liquid solid phase transition in free surface flow. This is one example showing ice cube melting in ambient air. Numerical result was compared to the images captured by thermal camera. After melting of 62 minutes by simulation, the result was agreeable with the experiment. This one is more realistic experiment. Ice pouring water on the ice cube placed in glass. So we have measured the melting front and remaining ice area in the experiment, and that was compared to the numerical result shown on the slide. Our overall predictions by lattice-Boltzmann method was were in reasonable accuracy comparing to the experiment. So now it's time to apply the method to real field problem. So problem is the open water forming mechanism in the outlet channel of the small hydropower plant. So what is the open problem? What is the open water? The Google says open water is a stretch of water which is not enclosed by ice. So our research question is, how does open water form in open channel flow? Can a simulation help to figure out the ice problem in a hydropower plant? So in this slide you can see open water in the biggest river of in Mongolia, December 2013, and photo below you can see the open water next to the hydropower plant. So this map of Mongolia shows location of the Tosun single hydropower plant, which is our study object in this presentation. So this slide shows an outlet part of the hydropower plant, showing computational domain including inlet and outlet boundaries and the ice cover. So we ran 3 cases of simulation, assigning 3 different time in the inlet boundary condition for water temperature, and the boundaries used for the simulation are listed in the lower right corner, and we set the ice cover at the low water level, so we had to find exact discharge to maintain low water level, because winter flow data was not available at this moment. So how much discharge do we need to maintain the low water level? First we run simulation with the discharge of turbine capacity. It was too high. Apparently the water velocity hits up 7 meters per second. So then we reduced the discharge until low water level is maintained, and we found that 0.87 cubic meter per second, and this discharge was used for 3 cases of run with the ice cover. So this is the result for 3 cases, showing remaining ice area. In the graph you can see case 1 shows that the system is equilibrium, because the remaining ice area is conserved. No melting and freezing was observed, but next 2 case shows open water forming with the transition points in remaining ice area. Case 2 shows that the melting until the open water and further freezing, while case 3 shows continuous melting during the simulation. This is the temperature field for 3 cases at 3 different times, and case 2 and case 3 shows the open water forming on the figure. This animation shows very moment of the initial opening for open water. For temperature of 4 degrees Celsius is high temperature in winter time, so this temperature can cause open water and further ice condition to worst if discharge is very fluctuated, not constant. But sometimes it is possible to get the temperature above 4 degrees Celsius because water is released from the reservoir. Temperature of 8 degrees Celsius is unrealistic in this case, but it helps to understand the phenomena. So this figure shows interpretation of the open water forming mechanism based on the numerical result. For example, there are four processes can be observed depending on water temperature and flow characteristic, namely ice warming up and melting process, second initial opening, and third the extending process, and then equilibrium process. So ice core in outlet is warmed up and melted with upward directed warm water flow until initial opening, which can be observed near to or far from the structure. Generally, open water forming in outlet of a hydropower plant is same as a natural river channel. After initial opening, depending on the temperature and discharge of water, one of extending process, for example, open water extending or ice core extending, will be observed. Those extending process directly leads the equilibrium state after uncertain time. For example, open water will be maintained during the several time, or open water is enclosed by ice cover, again at upper level or low level. This photo shows ice condition in hydropower plant taken 2014 and 2017, and photo below shows ice cover, ice open water was covered by ice, again at the lower level as explained in a previous slide. So in summary, we have proposed the numerical method using lattice Boltzmann method for liquid solid phase transition in free surface. This method is validated and applied to the open channel outlet channel of the dozen single hydropower plant, and numerical result can help to make operation plan to control ice in downstream of the hydropower plant. Based on the numerical result, we explained open water forming mechanism in open channel flow. In this study, ice cracking or crushing is postponed to the future work. As a take-home message, I would like to say all in one or a single lattice Boltzmann method is possible. In our case, free surface, liquid solid phase change, liquid solid interaction, fluid structure interaction was possible. So this is ongoing work. Animation shows the ice cylinder floating and melting simulation, and we are working on the 3D extension of the numerical method, and also doing a parallel code on the GPU machine. So thank you very much. Goodbye.